Hello everyone. The title of this video is the unit step function, also known as the Heaviside function, and the second translation theorem for Laplace transforms, which is a translation on the t-axis. I've done a video on the first translation theorem for Laplace transforms as well, and that was a translation on the s-axis. This one's on the t-axis. Alright, so first I'm going to talk about what is this Heaviside function or the unit step function. And then I'll go over several examples as to how to rewrite piecewise defined functions, certain piecewise defined functions, using this unit step function. Then we'll get into the second translation theorem for Laplace transforms and go over several examples of finding Laplace transforms and inverse Laplace transforms using this second translation theorem. Okay, so what is the unit step function? Now it's got this in the book I'm looking at, in some textbooks I've seen, the unit step function is labeled by this fancy script capital U. Alright, and then it's u of t minus a, where a is some positive real number. Well, this u of t minus a, this unit step function, is equal to 0 whenever t is less than a, greater than or equal to 0 as well. Some books extend this to just when t is less than a, but since we're going to be talking about Laplace transforms, we only require that the function be defined for values of t 0 or greater. So it's the function that's equal to 0 when we're less than some value a, and it takes one step up, a unit step up at a or greater. So the value is 1 when t is a or greater. So here's a graph of the unit step function, right, if the horizontal axis were the t-axis. So from 0 to a, right, the output 0, but not at a, right, got an open point there. And then I jump up when t equals a, the value of this function is 1, and it stays 1 for all the values beyond a. Okay? Now, why this is being introduced is because this function can be used to rewrite specific, to rewrite piecewise defined functions in a manner that's not piecewise anymore. So in a manner that has just expressions involving the unit step function here. Let me show you what I mean. Alright, so I've got a few examples where we're asked to write the function I'm given, the piecewise defined function, that's defined for t 0 or greater. Okay. In terms of the units, in terms of unit step functions. All right. So this first example, I have f of t equals 2 if t is from 0 to 3, not including 3, and negative 2 when t is greater than or equal to 3. Now let me just draw a real quick graph of f of t. So I'll make some axes where the horizontal axis is the t-axis. And then notice like there's zeros mentioned and then 3. And the value of this function is positive 2, but only for values of t from 0 to 3, so like this, but not at 3. And the value of this function is negative 2 for values of t that are 3 or greater. So like that. Right, but some horizontal segments, right? Okay. So we can express this function using our unit step function when a equals 3. Right, because you see the cutoff. Basically, where are the jumps made? All right. Where are the jumps made from one piece of the graph to the next? So here it's at 3. So let's see how this would work. Now, let's start off with f of t equals, then I write the first piece, the output for the first piece of this from 0 up to whatever, 0 up to 3. That's 2. So I start with the first piece, the piece that's defined at 0 up to whatever. First piece. All right, then I want to take that piece away. So what I'm going to do is this. I'm going to subtract 2. I'm going to subtract that piece, minus 2, times the unit step function of t minus 3. All right, because it cuts off at 3. Basically, I want to get rid of 2, get rid of the first piece after t equals 3. That's all this is saying. And then I would like to add the next piece, but only beyond t equals 3. So again, this is going to be multiplied by the unit function, the unit step function of at t minus 3. And again, here's the second piece, negative 2. So again, I start with the first piece. I take that first piece away after t equals 3. That's, take away that first piece times the unit step function at t minus 3. And then I want to add on the second piece after t equals 3. So I add the second piece, negative 2, times the unit step function at t minus 3. Now notice there are some like terms here. Right? Both of these terms have this unit step function at t minus 3 in common. So I'll put those together and just combining the coefficients. So we have here f of t is equal to the following. 2 and then minus 4, right? Negative 2 plus negative 2 is minus 4 times the unit step function at t minus 3. Okay, and if you don't believe this, right, then there's a way to write this function now without writing it in piecewise form. All right, this means the same as this. And again, if you don't believe it, let's put in just test some values out. Here, I'm going to test some values here and see if we end up with the same outputs. So how about if t were 1? Right? If t were equal to 1. Now, if you use the piecewise defined function, f of 1 would simply be 2. Right? But if we use this one here, f of 1 is going to be 2 minus 4 times u, the unit step function, evaluated at, 1 minus 3. So that's 2 minus 4 times the unit step function evaluated at, negative 2. So, basically, if this input ends up ever being less than 0, if the input of the unit step function after you plug in some value is less than 0, then this is going to be equal to 0. And if it's greater than or equal to 0, then the output for the unit step function is 1. Right? Kind of again going back here to our definition of the unit step function. Right, if I plug in a value between 0 and a, that's going to make this less than 0, and again output is 0. If you plug in a value greater than or equal to a, this input will be this expression in the parentheses will be 0 or greater, and you'll have an output of 1 for the unit step function. So you see what I'm resulting here, 2 minus 0 is 2, which is exactly what I needed it to be. Let me just test one more value here. What if t were 5? Well, again, you just look at the pieces. F of 5, that's 5, the input's greater than or equal to 3, so it's negative 2. But then going into the way I wrote it using the unit step function, we have f of 5 equals 2 minus 4 times the unit step function at 5 minus 3. Now, 5 minus 3 is 2. And again, if this input is greater than or equal to 0, if the number inside the unit step function is greater than or equal to 0, then the output of the unit step function is 1. So what I end up with here is 2 minus 4 times 1. That's 2 minus 4, or negative 2, as it should be. And you could test this out with more and more inputs, and you'll see that the function I have here involving the unit step function is exactly the same as the piecewise function I was given initially. All right, and then they have the same graph and everything. All right. But it's really as simple as that. You start with the first piece, take away the first piece after some value, add the second piece after that value, take away the second piece after. If there are more pieces, you just keep doing that, keep repeating that process. So for example, on my next example, I have a 3-piece piecewise defined function. So again, so far I'm starting off with some examples that are pretty simple with constants. So here this function is equal to 1 from t equals 0 to 4, not including 4. This function is equal to 0 for values of t from 4 to 5, not including 5. And the value of this function is 1 for values greater than or equal to 5. Right, so again, here's the t-axis. I'll make a quick graph of this. Now my cutoff points, you have 0, you got 4, and you got 5. And from 0 to 4, the value of this function is 1, but not at 4. Right? At 4, it jumps down to 0. But then it's 0, but not at 5. It jumps back up to being equal to 1, and then it's 1 forevermore. Right. Okay, so there's the graph of f. And again, I want to write this as a function involving those unit step functions. So first piece, I'll start with 1, and then I'm going to take away that piece after 4, right? So subtract 1 times the unit step function at t minus 4. And then I'm going to add the next piece, which is kind of silly to write, but I'm going to write it anyway. I'm going to add 0 after 4. All right, I want to add 0 after 4, so times the unit step function at t minus 4. And then I want to take that away after 5. So subtract 0 times the unit step function at t minus 5. All right, this takes away that piece after 5. And then I would like to add on the last piece, 1 after 5 times the unit step function at t minus 5. All right. And then obviously this can be simplified a bunch. These both have times 0, so those are not needed. Now, earlier I combined some like terms. Here, these are not like terms. These are two different unit step functions, right? This is the unit step function that's equal to 1, when t is 4 or greater. This is the unit step function that's equal to 1 when t is 5 or greater. Totally different, so I can't just add these. So this is it. F of t equals 1 minus the unit step function at t minus 4 plus the unit step function at t minus 5. And there you go. All right. This function here has exactly the same outputs as my piecewise defined function. Okay, and again, you can test some values if you wish. Plug in 3 for t, the output should be 1. Well, if I plug in, I'll just do one test value here just to show you. So when t equals 3, f of 3 would be 1 minus this unit step function at -1 plus this unit step function, again when t is 3, that's -2 in there. And as I mentioned earlier, if the number inside the unit step function is less than 0, then the output for the unit step function is 0. So both of these are 0, and I end up with just 1. Right. And try t equals 4, 4.5, and you'll get an output of 0. Try t equals 5, 6, 7, you should get an output of 1. Right. I promise you. All right. Okay, so hopefully, again, just working with constants here. Just got one more example where one of the pieces isn't a constant. All right. But it's still no different than the previous examples. It's two pieces. So here f of t is 0 from t equals 0 up to 3 pi over 2, but not including 3 pi over 2. And f of t equals t squared from 3 pi over 2 onward. And so it looks something like this. Right. If you were graphing, here's 3 pi over 2, and again it's equal to 0 up until 3 pi over 2, and then it's part of the parabola, y equals t squared, so part of a parabola from 3 pi over 2 onward. Again, this is a very rough sketch of that function. All right, so again, pretty easy to write using the unit step function. So f of t equals, first I start with the first piece, and then I take away that first piece after 3 pi over 2, right? So 0 times the unit step function at t minus 3 pi over 2. Now I know, again, it's still, you don't have to, if the function if the output is 0 on some piece, you don't have to worry about it. I'm just writing it for the teaching purposes. All right, and then I add the second piece, but again only after 3 pi over 2, so I'm adding t squared times the unit step function at t minus 3 pi over 2. And then get rid of the zeros here. So our function f of t can be written this way and has exactly the same meaning as the piecewise function. So 0 plus t squared times the unit step function at t minus 3 pi over 2. So t squared times the unit step function at t minus 3 pi over 2. And there you go. Here's a way to write that function without pieces and still has the same meaning as that piecewise defined function. Okay, so now why are we doing this? All right, well, first off, many functions are piecewise defined functions. And secondly, we're going to want to be able to take the Laplace transforms of piecewise defined functions pretty easily. And that's what this whole second translation theorem is about. All right, so let me get into the second part of this video is going to be on using this second translation theorem, which I just have written out here for you. You can go through your book and read over the development of this. If you remember the definition of Laplace transform, developing these formulas here from this theorem, it should be relatively simple with a pretty simple substitution. But I leave that for you to read. I'm just going to write out the formulas here. All right, so the second translation theorem has something to do with this, unit step function at t minus a. So here it is. So if capital F of s is the Laplace transform of some function little f of t, and a is some positive number, a is greater than 0, then the following. The Laplace transform of f at t minus a, this same little f here, times the unit step function at t minus a, right? So this would be the function that's value is 0 when t is less than a, and it's 1 when t is greater than or equal to a. So this Laplace transform is simply e to the negative a times s power, where a is this number here, the a, times f of s, times the Laplace transform of just little f. Right. And then of course you can go backwards, take the inverse, right? So the inverse Laplace transform then of e to the negative as times, capital F of s would be little f of at t minus a times the unit step function at t minus a. All right, and then an alternate method, an alternate version of this, I just replace f with g here. And if you make a substitution for t minus a in that, you'll get something and use the definition of Laplace transform, you can again, easily come to this conclusion that the Laplace transform of g of t, a function g of t, times the unit step function at t minus a will be equal to e to the negative as times the Laplace transform of the function g at t plus a. And as I put here, this is often easier to do, this alternative version of the Laplace transform involving the unit step function. I'll show you both, the first line and the third line here. I'll show you how to use both in a couple examples, but let's get into it. All right, so I'm going to keep this up on my desk, and let's get into some examples now. The first examples are finding the Laplace transform. All right, finding the Laplace transform. So what's the Laplace transform of t minus 1 times u of t minus 1 with the unit step function? All right, so if you look at this, now this is already set up nicely here. The function that's being multiplied by the unit step function is t minus 1. So I could think of that as some little function f of t minus 1, right? Where t's are replaced with t minus 1. And if that's the case, then little f of t would simply be t, right? And then if that's the case, the capital F of s, right, the Laplace transform of little f, remember the Laplace transform of t was 1 factorial over s to the 1 plus 1, or 1 over s squared. And you see I have f of t minus 1 here, the unit step function at t minus 1 here. It's got all the same features as this expression here, and the value of a is 1. Right? The value of the a is positive 1. So I can jump right to the Laplace transform. It'll be e to the negative 1s, right, negative as, times f of s, which is what we saw, the Laplace transform of t, times 1 over s squared. Okay, or just e to the negative s over s squared. And there you go. There's the Laplace transform of t minus 1 times the unit step function at t minus 1. All right, now there's an alternate way to do this as well. All right, we can use linearity and distribute this unit step function here and say this is equal to the Laplace transform of t times the unit step function at t minus 1 and then minus the Laplace transform of 1 times the unit step function at t minus 1. Right. And then using the alternate version of the theorem, this one here. So using this alternate version, in the first Laplace transform we have, again, a equals 1. Right, the value of a is 1 here. We have the unit step function at t minus a. And then the g of t that's mentioned in this formula is t. So according to this alternate version of the theorem, this first Laplace transform is going to be e to the negative s, e to the negative 1s, times the Laplace transform of g at t plus a. Well, what's g of t plus a? That's t plus 1. Right? G at t plus a, and a is 1. So g of t is t, g of t plus a would be t plus 1. And so we have here e to the negative s, and hopefully you know these Laplace transforms. This would be 1 over s squared, and then plus 1 over s. Right, the Laplace transform of 1. Alright, but then don't forget we have this now. Minus, and then again, I have in this Laplace transform, the g of t is 1. Right, the function that's being multiplied by the unit step function. So again, according to this rule here, this will be e to the negative as, e to the negative s, times the Laplace transform of, g of t plus a would still be 1. That's a constant, right? So we have minus e to the negative s times 1 over s. Well, after distributing and simplifying, we'd have e to the negative s over s squared, and then plus e to the negative s over s minus e to the negative s over s. So all I'm left with is this, e to the negative s over s squared, which is exactly the same Laplace transform I got earlier, using the first version of the rule. Okay, because I noticed that this is a function of t minus 1. This also had t minus 1, so I could just jump into this rule here. But you can also do it the way, in this alternate method as well. And I'll show you both for every example I have. All right. Okay. All right, so again, keeping this on my desk here. Next example. All right. So next example is, what's the Laplace transform of t times the unit step function at t minus 2? Well, if I want to use this first version of the theorem, I want to get an expression here, involving t minus a. I have t minus 2. I have t minus 2 in the unit step function. So I'd like this expression in front to also be dependent on the, have the expression t minus 2 involved, but it doesn't right now. But that's easy to fix. That's easy to fix. Just replace, t with t minus 2 plus 2, right? You can't just subtract 2 and, you have to add 2 as well. It's like you're adding nothing. So let's see what happens here. So this is the Laplace transform of, and again, t I'm rewriting as t minus 2 plus 2. And then this is being multiplied by the, the unit step function at t minus 2. Then I distribute that unit step function, and we have the following. The Laplace transform of t minus 2 times the unit step function at t minus 2. Okay, and then plus 2 times, using the linearity property of Laplace transforms, 2 times the Laplace transform of the unit of 1, times the unit step function at t minus 2. All right, now this, the first Laplace transform here looks like this, where you can think of this function here as f of t minus 2. Well, if this is f of t minus 2, then f of t must just be simply t, right? Because if I replace t with t minus 2, it gives me that. And we know the Laplace transform of t, we saw it already, it's 1 over s squared. And the value of a is 2 here. All right, so this first Laplace transform, based on this rule, would be e to the negative 2s right, e to the negative as, where a is 2, times fs, right, so over s squared. So the Laplace transform here is e to the negative 2s over x squared. Then we have plus, and then here the function is just 1, right? Here the function is just 1, and we know the Laplace transform of that, right, is just 1 over s, right? And don't forget the times 2 out front there. So I got 2 times 1 over s times e to the negative 2s. So 2 e to the negative 2s over s. And there we go. And if you want to put those together with a common denominator, you can. But it's just, it's not necessary. Okay. Now, again, alternately, let's start that over. Let me do that again. We can use this alternate version, right? And we had the Laplace transform of just t times the unit step function at t minus 2. So if I use this alternate version here, remember this function that's being multiplied by the unit step function, that's going to be the g of t. All right. So then g of t plus 2, because a is 2 here, I want g of t plus a. That would just be simply t plus 2. And then according to this rule, using a equals 2, this would be equal to e to the negative 2s times the Laplace transform of g of t plus 2, so just t plus 2. And these should be simple enough, right? This is e to the negative 2s. The Laplace transform of t was 1 over s squared. Laplace transform of 1 was 1 over s, so 2 would be 2 over s, right? For constants, it's very simple, plus 2 over s. And there you go. And this is exactly, see how easy that was, this, using the alternate method? This is exactly what I got here. Right, see, if you factor out e to the negative 2s, you'd get, times 1 over s squared plus 2 over s, exactly the same thing. All right, so like I said, very often this alternate version of the second translation theorem is going to be easier. Not all the time, but I'd say quite often. All right, so I've just got one more example. Where again I'll show you both ways to use the translation theorem to find this Laplace transform. Alright, so we have the Laplace, what's the Laplace transform of the cosine of 2t times the unit step function at t minus pi. So again, if I want to use this first version, I need to get this expression to have, be some function where it's a function of t minus pi. Now the value of a is pi, right? The value of a is pi. And to get t minus pi involved here, I'm going to do the following. I'm going to replace t with t minus pi plus pi, right? Kind of like in the last example where I did t plus 2 minus 2 or minus 2 plus 2. That way I'll get t minus pi involved in the function as it is in the unit step function. Alright, so here we go. We got the Laplace transform of the cosine of 2 times, and then we have t minus pi plus pi, right? Replacing t with t minus pi plus pi. And then we have times the unit step function at t minus pi. Alright, now let's take a look at this expression here for a second. If I distribute, that's going to be the cosine of 2 times the quantity t minus pi, and then plus 2 pi. Now, I don't know how much trig you remember, but if you take the cosine of some angle and then just add 2 pi to it, it's going to give you the same cosine as the original angle. Right? Remember the cosine of theta plus 2 pi radians is just the cosine of theta, and that's the same thing for any trig function. So this can be simplified then to just the cosine of 2 times t minus pi. 2 times t minus pi. Right, without the plus pi in there, because again, when you distribute the 2, you get plus 2 pi, and then I'll give you the same cosine. All right, then times the unit step function at t minus pi. Great, and now I have something that looks like what I want, where again, the value of a is pi. So this cosine of 2t minus pi, that's f of t minus pi. And if this is f of t minus pi, then f of t, just replace t minus pi with t, would be the cosine of 2t. And you should know the Laplace transform, capital F of s, of the cosine of 2t. Remember, that would be s over s squared plus 2 squared, or s squared plus 4. All right, and I've got a is pi. I know f of s. We can finish the Laplace transform now. So all said and done, this is equal to e to the negative pi s power, right? A is pi times fs times this s over s squared plus 4. And there's the Laplace transform of the cosine of 2t times the unit step function at t minus pi. All right, now again, I can do this in an alternate method. All right, I can do this in an alternate way, applying this, resorting to this formula here. So let me start that again. All right, or doing again the Laplace transform of the cosine of 2t times the unit step function at t minus pi. So this time if I just think, hey, what's the function that's being multiplied by the unit step function in here? Let's call that g of t. Right, g of t is the cosine of 2t. And then again, a is pi, the value of a is pi. So in the end, I need to know the Laplace transform of g at t plus a, or t plus pi. So if this is g of t, g at t plus pi would be the cosine of 2 times the quantity t plus pi, right? Just replacing t with t plus pi. And then just as before, when I distribute the 2 here, I'll have 2t plus 2 pi. Well, the cosine of 2t plus 2 pi would just be the cosine of 2t. So I can very easily simplify that. And that works out wonderfully. All right. So when I'm done here, this is going to be equal to e to the negative pi s times the Laplace transform. And the value of g at t plus a, the value of g at t plus pi we saw is just the cosine of 2t. And this is something you should know, right? This is again e to the negative pi s times. This is s over s squared plus 2 squared. And it's exactly the same thing I got earlier. All right. So again, either form, either version of the second translation theorem will work out. All right. So now I'm going to be taking inverse Laplace transforms. Right? So I'll be looking at this line that I wrote involving the inverse Laplace transforms. Let me just keep that line up top. Sorry, that's kind of bright. All right, there we go. All right, so this is the reversal, right, of our second translation theorem earlier. Just doing the inverse Laplace transform of e to the negative as power. So in all these, we're going to see some e to the negative number times s power times fs. Now f of s is going to be the Laplace transform of some function little f, and once we know little f, then we have over here little f at t minus a times the the unit step function at t minus a. That'll be the Laplace transform. Or the inverse Laplace transform, I'm sorry. All right, so here the inverse Laplace transform of e to the negative 2s over s cubed. Now if I want to write it this way, this is the inverse Laplace transform of e to the negative 2s, right, there's my e to the negative as, times, 1 over s cubed. So we can see from the way I've written it here, the value of a is 2, and the f of s, right, which is again the Laplace transform of some function little f of t, is 1 over s cubed. So what I want to find now is this, what's this f of t, so then I can state what f of t minus a is, or f of t minus 2 is. So in order to do that, I need inverse Laplace transform of the, I want to find f of t. So f of t, right, would be the inverse Laplace transform of 1 over s cubed. Well, hopefully you remember your Laplace transforms, basic Laplace transforms, inverse Laplace transforms. If I multiplied the top and bottom of this by 2, if I multiply the top by 2 and then I'll pull half outside, the inverse Laplace transform of 2 over s cubed was t squared. Again, I'm not going to get into all that, right? You should know those basic ones now, by now, I'm hoping. So this is just half t squared. That's f of t. That's the function whose Laplace transform is 1 over s cubed. All right, and then using the formula, using our second translation theorem here, this inverse Laplace transform is the following. F, little f at t minus a, well that's f at t minus 2, let's write it, f at t minus 2 times the unit step function at t minus 2. Well, what was little f? That was this, half of t squared. So this would be half of the quantity t minus 2 squared, right? Just go to little f and replace all the t's with t minus 2 times the unit step function at t minus 2, and there you go. This is the inverse Laplace transform of e to the negative 2s over s cubed. And if you'd like to verify this, if you'd like to check this, take the Laplace transform of this function. And the Laplace transform of this function should end up being e to the negative 2s over s cubed, and that's a way you could verify this. I'll leave that to you, though. All right, so let's keep going. I just got 2 more here. Sorry, I know this is a long one, but I did cover a lot, unit step function and second translation theorem and all that. All right, so again here, I'm going to rewrite this in the form that I want. We're doing the inverse Laplace transform of e to the negative pi s times, and then 1 over s squared plus 1. All right, so if we look at this and compare it to our little formula up here, oops, put that down. The value of a is pi, right, e to the negative as, pi s. And then the capital F of s, right, the Laplace transform of some function little f of t is 1 over s squared plus 1. So now I want to find f of t, right? F of t is going to be, the inverse Laplace transform of 1 over s squared plus 1. Now that should look familiar. I'm hoping you recognize this as the, the inverse Laplace transform of this function would be the sine of 1t. All right, so f of t is the sine of t, and then when I use the theorem, this inverse Laplace transform will be the the value of f at t minus pi, right? Because again, a is pi. A value of f at t minus a times the unit step function at t minus pi. And go to little f. That's the sine of t. So this is the sine of t minus pi times the unit step function at t minus pi. And there you have it. There's the inverse Laplace transform of the function we were given, e to the negative pi s over s squared plus 1. Now you could also say, hey, the sine of t minus pi, the sine of t minus pi is just negative sine t if you use the sine of a sum formula. So you could also say this is just negative sine t. This is using a trig identity, right? The sine of t minus pi is the opposite of the sine of t. So you could say this is equal to negative sine t times the unit step function at t minus pi. Same thing, right? They're the exact same function. All right. So I got one last application of this, and then I'll do a video after this where we solve some initial value problems where the unit step function will come up and junk like that. All right, so my last example, I have find the inverse Laplace transform of e to the negative s over s times s plus 1. So again, this is a inverse Laplace transform of e to the negative 1s times 1 over s times s plus 1. All right, so looking at this, it's in the form that I have here. The value of a is 1. All right, that's e to the negative 1s. And our capital F of s here is 1 over s times s plus 1. And what I'm going to do is use partial fraction decomposition to break this up. All right, so this is some constant a over s plus some constant b over s plus 1. Multiplying by the denominators, we get 1 equals a times s plus 1 plus b times s. And if s were 0, you'd see that a was equal to 1. And if s were negative 1, you'd see that b would have to be negative 1 as well. All right. So this 1 over s times s plus 1 is 1 over s minus 1 over s plus 1. And you should know the inverse Laplace transform of this. That'll be the f of t. Right, coming down here. So little f of t is the inverse Laplace transform of these. Well, the inverse Laplace transform of 1 over s was 1 minus, and then the inverse Laplace transform of 1 over s plus 1 would be e to the negative t. Right. And then I just need to replace t here with t minus 1, right? Because when I apply this formula, when I apply this theorem, this will be equal to f at t minus a, so f at t minus 1 times the unit step function at t minus 1. And this was f, so this is equal to the quantity 1 minus e to the opposite of t minus 1, right? Or you could put 1 minus t if you distribute the negative, times the unit step function at t minus 1. And there you have it. The inverse Laplace transform of that function of s that we were given. And once again, if you wish to verify this, take the Laplace transform of this function here, and you should get that function back, e to the negative s over s times s plus 1. But I leave that to you to verify. All right, so again, lots of stuff, right? The unit step function or the Heaviside function. Very important in being able to rewrite piecewise functions, right? You should be able to rewrite piecewise defined functions that are defined on the non-negative reals. You should be able to write those in terms of using some unit step functions, as I did in my first couple examples. And then hopefully you read through and understand the second translation theorem, both versions, and are able to apply that to find the Laplace transform or inverse Laplace transform of certain functions. All right, and hopefully watching me go over these several examples helps you out when you're looking at problems like this on your own. And thank you very much for watching.